Hi, this is Mathematics for Social Justice by Mark Roth. This is a rhombi-Cauchy dodecahedron. This particular one was partially dismantled, but it was complete before. It was built by a student of mine named Exie. And I want to talk about certain counts that you can do when you're working with Platonic solids and Archimedean solids. This is an Archimedean solid. It's got all the corners are the same, and so we have pentagon, square, triangle, square, in this order at every vertex. And so it's an Archimedean solid. There's 13 of these. There's 5 Platonic solids where you're using all triangles or all squares or all pentagons. There's interesting counts that you can make. For example, not every teacher knows actually that you can count the vertices quite easily. So let's talk about the cube. If you look at the 3 squares of a cube that meet at every corner, but you lay them flat on the table, you can call this like an angular defect. And this is 90 degree. Now if you take that 90 and divide into 720, it's always 720, you get 8. And 8 is the number of vertices, or corners. And you're all familiar with cubes. You know a cube has 8 corners, right, or 8 vertices. Let's look at a tetrahedron. So a tetrahedron would be an equilateral triangle, then another, and then another. The angular defect is 180 degrees. And if you divide 180 again into the same number, 720, you get 4. And a tetrahedron, which is also a triangular pyramid, has 4 corners. Now, this works for the Platonic solids. It also works for the Archimedean solids. So it would work with this. We would have a square. Then we'd have a triangle. Another square. And then a try to draw a pentagon. That's not a very good pentagon, but the angular defect would be we have to add up 2 90s, a 60, and a 108. So that's going to be 180 plus 168. And so if this was 180 twice, we'd have 360, but we're missing 12. So we would have to divide 12 into 720. And we get 60. So that tells you this complete structure, rhombi-Cauchy dodecahedron, would have 60 vertices, or 60 corners. But then how would we go from there? So I just write V for vertices equals 60. Now I'd like to know, let's say edges next. How many edges would it have? If you look at this, every vertex is connected by 1, 2, 3, 4 edges. And we call that the degree. So if you have a vertex and it has 4 edges, we say the degree is 4. Okay, so that's how many, think of that as a town and these roads. And 4 roads leave each town, so the degree is 4. And we know there's 60 vertices, right? So there would be, so the degree of all the vertices would be 60 times 4, 240. Now, each edge has 2 vertices. So just look at an edge. You know, it's got a vertex on one side, a vertex on the other. So that means if the edges altogether have to have 240 vertices, each one has to have 2. So 2 goes into 240, 120. So this has 120 vertices. Now, is there another way to do that? Well, yeah. And I think this way Might be original with me, I'm not sure. But let's think of a fight. So it's a play fight. We're not serious about a fight. But suppose the edges and the vertices are in a fight. So what's going on at each corner? So again, we have, suppose the edges and the vertices have equal strength. So it looks like 4 edges are ganging up on one vertex. But don't forget, the edge has to split its strength because it also has to send half its strength over here. So this is a half, a half, a half, and a half. So that's 4 halves, which is 2. So that's another way to double this and get this. But we can also have a situation where there's only 3 edges at each point. So then we have a half, a half, a half. And in this case, it's 1.5 against 1. So in this situation, you would take the number of vertices and times by 3 halves. And finally, you can have this situation where you have 5 edges at each point. So it'd be a half, a half, a half, a half, a half, ganging up on 1. So in this case, there would be 2.5 times as many edges as vertices. So now to calculate the faces, well, we could use Euler's formula that when you have something that's homeomorphic to a sphere, which means you can gradually transform this Archimedean solid into a sphere, that in that case, vertices minus the edges plus the faces equals 2. So in this case, we would have 60 minus 120 plus the faces equal 2. So that would be 62 faces. So F would be 62. So now let's try to figure out how many of each kind of polygon there is in this rhombic dodecahedron. It turns out there's 1 triangle at each vertex. But that doesn't mean there's 60 triangles because each triangle touches 3 different vertices. So we have to divide by 3 and get 20 triangles. And let's take another look. You can see that there's 1 triangle at each vertex. But if you look again, you see 2 squares at each vertex. Now, if there was only 1 square at each vertex, you would divide 60 by 4 and get 15 because a square touches 4 different vertices. But since there's 2 squares at each vertex, we got to take that 15 that you get from 60 divided by 4 and double it. So it's going to be 30 squares. And then by process of elimination, there's going to be 12 pentagons. So doing these calculations would be good. This would be a good exercise for students in a class, and they would have fun making the different Platonic solids and Archimedean solids. And then they can do these calculations. It would be a good lesson in a school and a fun one. So that's all for this, and thank you for watching.